Hello everyone, my name is Nizak Patel and today we will be going over the assignment 2 of Applied Machine Learning. So let's get started. So in this assignment we are working with the iris dataset. So we first need to import the iris dataset. We are not allowed to use the inbuilt iris dataset that is obtained through the Keras. We need to work with the one that is provided. So first of all, it asks us to upload the iris.csv into the Google Drive. As you can see, I already uploaded the CSV file here. Now to read the file from the Google Drive, we need to mount our drive into the Google Colab. So for that we are doing from google.colab import the drive, and in the drive we are using the mount directory to see the content of the Google Drive. Now we need to find the path of the CSV file and save it in a variable called file name. So for that we can do file name equals to then the path of the CSV file, so it's /content/ the file name. Now we need to read the content of the CSV file and save it in a variable called iris. So for that we'll do the read CSV method that is provided in the pandas. So we are importing pandas as PD, and using that we can read the CSV file, which is this one, by providing the file name and storing it in a iris variable. So to ensure that we have imported the CSV file in this iris variable, we can see the first 4 or 5 rows of this data set. So for that we can use the header method, which shows the 5 rows of the data set. So as you can see, we successfully imported the CSV file. Now this in all the columns have the numbers in each row, but the species column have a name in that. So we need to convert these names into some kind of numbers. So for that what we will do is we will do setosa as 0, versicolor as 1, and virginica as number 2. So to map these names into the number, what we can do is we can just override them. So we can write the species column as the original species name dot map, and in the map we can set the setosa as 0, versicolor as 1, and virginica as 2. By doing that we can ensure that if the renaming of these variables is done correctly, we can just see the first few rows of the data set. So as you can see here, we successfully converted the names into numbers. Now in the next section we need to select the first 4 columns of the data frame as data and call the data X. So to get the first 4 columns we can use the ilog. In the ilog, the first part is for the rows, so we are getting all the rows. The second part is of columns, so for the columns we are getting the first 4, so starting from the 0 till the 4th one, and dot values will give all the values of that column. So just printing the variable, we can see we got all the results here. Now moving on, in the next part we need to select the last column, so doing same as before, but this time in the column section we can do -1. So the -1 will select the last column. and here just printing out this variable, we can get the result as below. Now in the fourth section, we need to split the data X and the label Y into the training and testing segments and call this as X-train X-test, Y-train Y-test. So for this we can do the same thing as we have done earlier in the earlier semester by using the sklearn and using the train test split module. So for that we can do X-train X-test, Y-train Y-test, and we will assign all these variables by splitting the data. So for that, train test split method and then passing the X and Y, and here we need to make some changes. So it's mentioned here to take the test data as the 20%. So for that we can specify test size which is equals to 0.2, that is 20%, and we need to use random state which is equals to 123, so specifying that here. Now we need to check the first 5 rows of X-train X-test, Y-train Y-test. So for that, doing the same thing, X-train starting from the 0 till the 5th row, so 0 to 5, and then doing it for the X-test, same thing, 0 to 5, we can get this result. For the Y-train, which is our labels, 0 till 5, so here we get all the labels, and same for the X-test, 0 to 5, we get these labels. Now we need to check the length of the X-train and X-test. So if it's 120 and 30 respectively, then it's good. So let's check that using the len function. So len function passing X-train, we get 120. So in the first part we are good. For the second part we can use the len method, and here passing the X-test, we get the 30, so which is here. So now we can move ahead and do the rest of the operation. In the fifth section we need to convert the Y-train and Y-test into categorical and call them one hot train label and one hot test label respectively. So for that we can use we can import the two categorical from the Keras library, and we can use these two categorical to assign one hot train label and test label. So for the train labels we can use the X and Y train, and for the test one we can use Y test. Now the real fun part begins. We need to define a model. So this is the first part. So in this we need to use 3 dense layers, each one with the 100 hidden units with a value activation function, and 3 as the number of output in the last layer. So we can use the activation as softmax here. So here we can see we are importing models and layers from the Keras, and then we can define our model as model.sequential and adding 3 layers. So model.add, in the first layer we are using the 100 units, so we are specifying 100 here, activation as value, and input shape as 4. In the second one we can use the dense layer with the 100 units and the activation as value. In the last layer we can use the 3 units and activation as the softmax. Now we need to compile this model using the RMS prop, the appropriate loss function, and accuracy. So here we are using the categorical cross entropy, so defining the loss, optimizer, and matrices. Now it's time to fit our model with the 20 epochs and batch size as 10. So as you can see we are doing model.fit with the X-train one hot train labels, epochs equals to 10 and batch size epochs 20 and bed size 10. So by seeing the result, we can see that gradually the accuracy increases up to at certain epochs, and then the result is not steady. It's like one is higher, one is lower, then other is lower, then it's higher, but we can see the loss is decreasing, which is a good thing. So for this one, we are getting the maximum accuracy of 98%, which is at the 13th epoch. So moving on, we can calculate the accuracy of this model by using the model.evaluate. So by testing, we can get the accuracy as 0.866 and loss as 0.192. Now in the second part, we need to do the exact same thing, but now using the 10 hidden units with a ReLU activation function, and we just need to use the three units in the last layer. So doing same thing as before, importing and defining the model, defining the units as 10. The rest everything is similar. Then in the compilation, all the parameters are same, but here we'll change the epochs as 4 and keep the batch size as 10. So by doing so, we can see that we get accuracy till 61%, but here we can have a very good amount of loss. We can calculate the accuracy for this model as well. So we can, the accuracy is 0.800 and loss is 0.89, which is tremendously high as compared to the earlier model where we are getting 0.19 as the loss, and here we are getting 0.89 as the loss. So what do we learn from these two things? So the first thing we learn that by changing the number of hidden layers, the hidden units, the accuracy and the loss is drastically affected. Then what have we learned? So it can also lead us to the overfitting. So if you set more epochs, then there will be a chance of the overfitting, but if you use the less epochs, then the overfitting is less, but we will face the information bottleneck, which is the loss of the information for permanently. Here I have written the answers for some of the questions. So do we always suffer from overfitting? The answer is it really depends. Like when a model has too many parameters in relation to quantity of training data, then there is chance of overfitting. So how can we manage this overfitting? We have learned several methods, like we can use cross validation, dropout, then regularization. Also we can remove some of the layers and the amount of units of that layer. Then what can we do? We can also use the early termination, that is using less amount of epochs. So that's some ways to manage the overfitting. Now what we need to do is we can play around with this. So changing the hidden units, layers, the compilation parameters, number of epochs, and let's check what happens. So for this purpose I have used 4 layers this time. So 4 plus 1 is the softmax, so in total 5 layers, keeping 100 as the hidden units. Rest everything I have kept the same, the compilation parameters, and here the epochs I'm changing it to 10. So we already learned that to deal with the overfitting, we can do the early stopping of the early termination. So let's see what happens here. So as you can see, we are having the accuracy gradually high. So it's not the case that we faced earlier. In there we were having accuracy maximum till some point, and then it was not consistent. Here as you can see, it starts from 0.57 till 0.97. So that's very good. And here the loss is 0.119. By testing the accuracy here, we are getting the test accuracy is 0.966 and loss is 0.131. Let's compare with the earlier model. That's the first one. In the first one we are getting 0.86, and in the one that I defined we are getting 0.966, which is very good. So this model works very well. So talking about the loss, in the previous one we were getting 0.192, and in the last one we are getting 0.131, which is also very good. So which means this kind of model works really best. So this can prove the point that having more layers can help to deal with the overfitting, and which can improve the accuracy of the model. And using the less number of epochs can also help in training the model. So that's everything for this assignment, and see you guys in the next assignment. Till then, take care.